So, Om Namah Shivaya, Namaste. Hello everyone who has come here. Thank you very much for coming here to listen to me. I hope everyone can hear me from the back also. I don't need a microphone. So my name is Ayush. I am currently in the 8th standard, and today I'll be talking about some things in the field of mathematics, and I'll explain this topic called calculus. I will try to explain. Now, I may introduce a bit of myself. My mother used to work as a volunteer teacher here in Nachiketa. That is how I have experience. I've come to this school many times before. And I am very interested in mathematics. I'm very passionate. And I have participated in various competitions. I participated in this year's IUQM mathematics exam, and in the Zonal Informatic Olympiad this year, I got national rank number 7. So I'm competing currently, working on for the next level of the exam after the informatic. So today, I will teach you one interesting mathematical topic called calculus. That is the subject for both today, and hopefully we plan another section maybe tomorrow or very soon, Monday. Another session like this where we'll elaborate on this topic of calculus. Now, how many of you, first let me ask, raise your hands if you are in 8th standard. Many, and raise your hand if you are in 9th standard. And in the back 10th standard they will be. So, many students of all the ages, that's very nice. And how many of you have ever heard this word, calculus, before? So, a few have heard of calculus, but usually when you hear this topic of calculus, people say this complicated topic, difficult, but it's actually a very simple topic, and I hope to make it simple and understanding for you today. Before I explain the actual mathematics in calculus, I will explain history. So, calculus comes from Roman word calc, and calc in Roman language, Latin language, it meant small stone, pebble, small stone. And you know in abacus you will use these small stones to count numbers, to do arithmetic. So over time, from that word small stone, calculus used to mean in general all sorts of math, because you would do math with the small stones. So all math came called calculus. This is why people say calculation means doing math. But now in the more recent times, calculus has meant to be a very specific type of math. So what calculus means now is a specific math related to study of change. So calculus is to do with changes, small changes in things, and how to find those changes. So it has a very long history. So originally in ancient times, ancient Indian, ancient Greek, ancient Persians, there used to be many people who would use basic principles of calculus. They did not call it calculus then, but basic idea of change, they would use to find area. You might have learned in lower standard circle की area pi times r square. You may have heard this formula. Have you all heard this formula? Yes. But have you ever thought where this formula comes from? How do we know circle की area is pi r square? Ancient times, the mathematicians figured this out using calculus techniques. And later on, Indian mathematicians like Madhava used calculus to approximate things in trigonometry. They use a very advanced concept called Taylor series. Taylor series is named after some British person, but Madhava in Kerala, Indian mathematician, actually discovered Taylor series 500 years before Taylor himself. So calculus has a very old history, but modern calculus was developed by two people. One was Isaac Newton. Have you all heard of Isaac Newton in physics class? Yes. Newton did a lot of things. You may heard he was good at physics, science, but he also was very, very good mathematician. And so, in his own letter, in his diaries, he would develop the concept of calculus on himself when he was very young in quarantine. But he was in his own letters, he did not share it with the world. So, 10 years later, one German scientist comes and his name is Gottfried Leibniz. And Leibniz develops the theory of calculus on his own and shares calculus to the world. He publishes this. And then Newton says, wait, no, I had discovered this myself in my own letters. I have made this first, it is not fair, you are publishing it. So Newton and Leibniz got into a very long argument who developed, but now we say these two independent invented what is now called calculus. So now I've talked about history for a while. Now maybe I can talk about the actual subject. Calculus is a study of change, and the two main subjects in calculus are called differential and integral calculus. Differential calculus is based on how you can take something and find how it changes. Integral calculus is based on if I know how something is changing, how can I add all those up to figure out the bigger picture. Now today we will try to work on differential calculus, and I'll give you a simple problem. I am running 100-meter race in 10 seconds. Now what is my speed of the race in meters per second?
10 meters.
Obviously, you just divide 100 by 10 to get 10 meters per second as the average speed. And now what's interesting about this is I can plot this on a graph. I hope some of you are familiar with plotting on a graph. How many? The concept is we can take on this axis the speed, the time which we've taken. So 0 seconds, in the middle 5 seconds, in the middle 10. And this is the time in seconds. And on this axis is the distance that we cover in meters. And then we can draw this line. Are you all familiar with these type of graph plotting?
Yes.
Yes. So simply at any particular point you can figure out how far this person is. And this is a straight line from this point to this point. We know after 0 seconds he had covered 0 meters, obviously. After 10 seconds he had done 10 meters, and we are plotting a straight line between 2 points. Now, do you all know the equation of a line? Any of you? 10th graders. The equation of the line y equals mx plus b, or maybe it might be written in a slightly different way. But are you all somewhat familiar with y equals mx plus b? Maybe some of the higher grades may be familiar with this, but this essentially is a formula for how fast we may be at a particular point. B we can eliminate right now because B controls how high you are when you start. But at 0 seconds you are 0 meters, so we don't care about B. Y equals mx. M is essentially the slope of the graph, or the speed of the graph. Y is the distance in meters and x is the amount of time. And formula linking to these two is, in this particular example, y equals 10 into x. So like this, I can see that after 10 seconds you would cover 100 meters. After 5 meters, ideally, 10 times 5, so we get on this side, we would cover 50 meters. After 5 seconds, 50, 3 seconds, 30. We plot this perfect straight line. Now, if we have a line like this, do you know how to calculate the slope of the line? Anyone? Anyone wants to show the formula for finding the slope of a line? So, I will show you the formula. The formula is basically you take 2 points on the graph like this, 2 random points that you know. And then what you have to do is, you find the vertical distance, which is called rise, and you find the horizontal distance, which is run. And then you take rise over run to give the slope. We were already doing this before, taking vertical divided by horizontal 100 over 10 to get the total slope. But we can write this more general formula. if I have a point here which is at length on this side x1 and height on this side y1, I can write it like this, and this point is at time x2 and y height at y2. I have these 2 points and I have x1, y1, x2, and y2. I can then write a formula. Yes, that I asked if you are familiar with the slope formula of u. Of course, you will be familiar with this y1 minus y2 over x1 minus x2. You can also write y2 minus y1. If you do the same thing on x's, it will be the same. y1 minus y2 over x1 minus x2. This is the, in general, slope formula. Now, I am going to ask you a simple question. Do you think this graph is real? Do you think as soon as I start a race, I instantly start going with constant speed until I reach the end of the race? This will not happen in real life, correct? When you start a race, you will start moving at 0 speed. And at the end, you will be going high speed because it's a short race. You will continue accelerating until you reach finish line. So maybe instead of this, the real race graph plot would look something like this. Yeah, parabola, very nice. In fact, I chose these 10 seconds, 100 meter values because you can write this parabola perfectly as y equals x squared. This is a more realistic graph of the thing. Parabola, nice observation. And at the start you have a low speed, and at the top you have much higher speed than the average speed. If you average the speed, you get 10 meters per second, but the speed at a different point is now different. Now, calculus is the study of change. So, the question that I, as a calculus student, now want to ask is, if I have this function, y equals x squared, then is there a way for me to find how much it is changing at any particular point? How much is the distance changing at any point in time? That is the question that calculus helps us answer, and this is Newton's key contribution. So, I have this curve, and first thing that I'll do is I'll rewrite the slope equation. I'll rewrite it into a different form where I get the same result, but allows me to do more math. First off, instead of taking x1 and y1, x2, y2, what I can do is, instead of writing these as x1 and y1 separately, I can use the function notation. So I can write this as f of x equals x squared. This function notation, are any of you familiar with? Of course. So the concept here is, for the lower standard students, that f of x is a function machine. So it is equal to this number that I put in squared. So I can write f of 2 and the answer will be 4. F of 3 answer will be 9, like this. So instead of writing x1 and y1, I can write x1 and f of x1, which we know will just be x1 squared, which we know will just be the height on this graph. So f of x is x squared. You can just remember this if you're unfamiliar with this notation. So now we have x1 f of x1, x2 and f of x2. We only need the x values. The second thing I will do is that instead of thinking about x1 and the second x2, the two x values, I will think about the x and then this distance, the run distance. So I will call this special distance d for distance or difference. And often in calculus you will see this written as dx with a small x because it is the distance on the x-axis. So now if I have this point of x and we are moving dx, what will this be? X plus dx, right? It will just be x plus dx. So now I can replace x1 with just x because there's one x value, and x2 I can write as x plus dx. And as I mentioned, you can swap these values. If you swap numerator denominator, they'll be the same. So on the denominator, I will just write x plus dx, which is mix1 minus x2 being x. Now obviously you can see what this will be equal to that. Dx. X plus dx minus x is just the d. We are adding and subtracting x. And this is easy to see because this is the run value, rise over run, and the run distance we've defined to be dx. So then we've rewritten this denominator to be the dx value. Now numerator, the first y1 value will be of this point, the function value. So we can take f of the x position, and the x position is x plus dx. And we are subtracting from the first value, which will just be f of x. So we have this rewriting of the function. Instead of taking y, I am taking the f value of the x. And instead of taking x1 minus x2, I am taking a single x and the distance from x to x2 and using that. So this is the same as this if you put the right x and dx into it. Now, if anyone has some difficulties, I'm open to questions. Does anyone not understand this? Seriously, raise your hand if you have any doubts. So, I will show this simple example with this graph we have, the straight line, because it's easy to understand. Let's say that after 3 seconds you have calculated crossed 30 meters, and after 5 seconds you have crossed 50 meters. What is the slope? Well, you can take the difference d between 5 and 3 as just 2. So when we take f of, in the denominator, dx is just 2. And the first x is 3. So f of 3 plus 2 minus f of 3 over 2. So this basically is the answer to the question. What is the average speed between 3 seconds and 2 seconds after 3 seconds? This function will calculate. And we can plug in the linear values. So f of 3 plus 2 is f of 5, which is 50. And we subtract f of 3, which is 30, and we divide by 2. This is 20 over 2 equals 10. 10 meters per second on this straight line model, which we calculated by pure logic earlier. The average speed will be 10 meters per second. So do you understand that this is equal to this? Does everyone get it? If you have any doubts or not understanding, please just raise your hand. Okay, everyone understands? Good. We have this rephrasing of the slope, which is this. X plus dx minus f of x over dx. Now, the thing about calculus is, as I mentioned, what we want to find is change. The change in a speed at a particular point. So on this x square wala, the parabola graph, the question we want to answer is, at this point, how fast is the distance changing? So we want to find the rise over run at a particular point. But that is just the distance. So what we can, that's just the slope. So what this amounts to is, we want to find the slope of the function x squared at every single point of the graph. Find the slope is 0 here, the slope is high here, and we want a formula for finding that slope. This formula for the slope at a point is key to calculus. Now from this point, this formula, can anyone think of how to find the slope at exactly one single point? To use formula, we needed 2 points to find the slope. With this f function, new phrasing, how to find the slope at one single point? Can you figure out how to do this? Okay, you I see has been paying very attentively, have making notes, a lot of notes. So we have this function for finding the slope, and what I want to do is, can you think of a way to find the slope in exactly one point of this function? See, we only have one x. That's the interesting thing. We do not have x1, x2. So for x, I can plug in the point where I want to find the slope. May I ask why you're laughing? Okay. Are you all understanding what I'm writing aside here? So the issue is the dx is the gap between the 2 points. We are still measuring 2 points with distance dx, but I don't want 2 points, I want 1 point. The solution is to make dx 0. But then there's a problem. We cannot divide by 0. Here we are doing division by dx. But dx cannot be 0. But dx is the gap between 2 points and we want gap as 0. So this is very ingenious of Newton, very ingenious of Leibniz. This is why it took so long for this to be invented. The amazing mistake is that you can just say dx is very small. It is not 0, but it is a very small number that goes towards 0. So what you can say is dx says 0.0001. Then we are not measuring slope at 1 point, but we are measuring slope at 2 points that happen to be 0.001 apart, which is effectively the same as measuring at 1 point. Now the 0.001, the value is not important. What we will do is we see what happens when dx goes towards 0. And you will see what I do when I evaluate in the example for x squared. So what I'll do is I'll solve this problem for x squared and show how you can find the slope at a point. So this f of x, we put this with x squared. So f of x plus dx, we change to x plus dx the whole square minus x squared over dx. Now, who in the front row here, the 8th grade section, knows x plus dx the whole square? Yeah. So this will be x squared plus 2x dx plus dx squared. But we are subtracting x squared here, so we ignore the first thing. So numerator comes out to be 2 times this. So 2x dx minus plus dx squared, and we divide the whole by dx. So now what we can do is we cancel dx from here and here and here, and dx squared over dx is just dx. So this comes out to 2x plus dx. But remember what I said, dx is very small value. Now it is not 0 because we are dividing by here, we cannot divide by 0. But it is so small that Newton's ingenious trick was, if it's so small, ignore it. So dx we cut off from this value and the final result comes out to be 2x. Now notice what we have done here. We have taken this formula which calculates slope at 2 points, which is dx apart. Then we let dx be a very small value. Infinitesimally is the word here, infinitesimally small value, and we do the evaluation and we get answer 2x. And this is what is called the derivative. This is a very important term in calculus, and what we've just done is define the derivative. The derivative is the slope of a graph at a particular point. And we have found that the derivative of x squared is equal to 2x. So in other words, the rate that x squared is changing at a particular point x is equal to twice that x. So now you can do some simple maths. For example, here at x equals 0, 2x is also equal to 0. My slope is 0. So when I start the race, my slope, my speed is 0. Makes sense. But at the very end of the race, at x equals to 10, 2 times 10 is 20. So the end of the race, I am moving 20 meters per second. So this formula calculates the speed at any point of the race, provided that the distance is x squared. This is what I mean by calculus is the study of change. We have taken a function and find out how fast it changes. So the derivative of x squared is equal to 2x. And a definition of a derivative is take this and make dx become very, very small until it is effectively 0 and cut off the terms. Anyway, so now we have defined the derivative. This is an important concept, and I'd like any of you to raise your hands if you did not understand what a derivative is. Oh.
Can you calculate the exact point of the x0 square?
What do you mean by x0? Can you repeat your question?
How can you calculate the exact point from 0?
Exact quantum from 0, as in you want to calculate how we got the 2 into x in the solution to x, where we find the x. Is that your question? 2x is just a result from which we can put anything we want. The value of x will be given in a problem statement. For instance, your runner is running at a thing defined by the function f of x equal to x squared. How fast is the runner running after 3 seconds? If your problem is that, then you can do this computation. Find that the speed of the runner at any amount of seconds is 2x. And the problem says after 3 seconds. So 2 times 3 is 6. The runner is running at 6 meters per second. Anyone has any further doubts? That's a good question, thank you. Anyone has further doubts? Just raise your hand. Great. Everyone is clear with this concept, I hope. So, we have this technique by evaluating this definition of the derivative to find the derivative of some basic functions. And now what I'll illustrate is, instead of this computation algebra, this algebra you might say was very hard, right? If it was not hard, even for the 10th graders who understood it, the algebra was boring. So what I will do now is show some more intuitive ways for some particular formula. I'll show you something called a power rule for derivatives. So, now we take the function x squared. Now, when you have x squared, do the following. See, here is x squared. Now, this is the result of our function, x times x squared. The area of this square is the result of our function. You can think the distance the one has covered. And when you think of this dx value, you should think of how we are increasing x by some tiny value dx. I am making dx quite large here, so you all can see it. But dx would be quite small, very small, close to 0. So the question is now, if we have increased the borders of the square by dx, how much has the area increased? Now you can do the algebra, or you can see simple this thing. This has side dx and side x. So the area of this one is x dx. This is the same, x and dx, this rectangle. So the area of this rectangle is x times dx. And this tiny square here has side dx and dx. So the area will be dx squared. So we've come up with the same thing we did previously with all the algebra, but we didn't do any algebra. Now, we can see that when all of these you add up, x dx plus x dx is just 2x dx plus dx squared. But remember, I am adding dx to this. But in the end, we have to divide by dx. So what I'll do is, I'll just rewrite dx as dx squared. I'll just write dx. And we are dividing the whole by dx. So this gets cancelled and this gets cancelled. And as before, we get 2x plus dx. But dx by itself is very small, close to 0. So we can ignore it and we get 2x. This is an important point. Before we had dx squared in the thing, but that gets very small. It gets cancelled out and we ignore it. If we only have one dx, then we are dividing by dx anyways, and dx by dx is 1. But dx squared by dx is 0, and dx cubed by dx is 0, and any high powers of dx will get eliminated completely because they go to 0. So this, using geometry, you can figure out what the derivative of x squared would be without doing much algebra. Now, once we have done this, there's very natural next step after finding the derivative of x squared is to continue on by finding the derivative of x cubed. And again, I am literally just going to draw x in a cube. With all sides x, and the volume of this cube is going to be x cubed. Now, the question you have to answer is, if I add some extra dx to the 3 extra open spaces of the cube that you can see, I add some extra dx to make this bigger cube. I have this larger shape. Now, what is the total volume of this? How much has it increased? Now you can see on this side, we have increased it by dx on this top face. So we have added some extra dx towards it as a plate, and you can see, you can think of this as a cuboid where the height is equal to dx and the area of the base is x squared, because x squared is the area of the face of the cube, and that's how we're extending it. We're extending the x squared face by dx. So the volume that we get would be x squared dx. But this is not just happening on this face. We are adding dx to each 3 sides of the cube with breadth and height. So it will not just be this, it will be 3x squared dx. Now, you can see that just adding these 3 plates will not actually be complete. If you see, this is a side drawing of a cube, and you can see what we've calculated is just the volume of this plus the volume of this plus the volume of this. And you might rightfully say, we are missing this portion. We are missing this portion. We are ignoring this portion. But the thing is, these portions will all have dx squared in the evaluation. And dx squared over dx is 0. So we can ignore these and only focus on this. So the 3 plates we have go to 3x times 3x squared times dx, and when we divide, we cut out the dx, so we are left with 3x squared. So I will just write on the corner here the formulas we are aware of. We can see that x squared is equal to 2x, x cubed is equal to 3x squared. Actually, I can add one more function here, x. X is just a straight line. Y equals mx plus b, you can write x is 1x plus 0. And what derivative is just the slope, 1x plus 0. The slope in that is just 1, which I can just write here 1. So these are formulas we are aware of. The derivative of x squared 2x, x cubed is 3x squared, and x, the slope of the graph x, is always 1 at every point, has the same slope everywhere. Now question is, can anyone guess what the derivative of x4 is based on a pattern?
4x cubed. 4x
power n is, can you see the pattern here? X to the power n, where n is some variable. Nx power n minus 1. Yeah, plus. Because x square, x cube, we are taking square. X4, we are taking cube, and so on. So in general, xn is 2 for n x to the n minus 1. Now, it's complicated to prove, but this is called a power rule. Using the same logic here, this is true for every positive whole number. Once you show this positive whole number, you can show it's true for negative whole numbers. And then you can show it's true for any rational number. So, this is true for essentially whatever value of n you put in. This derivative of xn is nx to the power of n minus 1. And this is the power rule. Because we are taking x raised to some power. So what we've done is we found a way to find the slope or the rate of change of infinitely many functions, any x raised to some power. And now you can start doing some basic intuition about what this looks like. For example, you can look at this and let's say I have x cubed plus 2x squared. What will be the derivative of this function together? Well, you will try to calculate, but you intuitively know what to do, right? Intuitively, what you can do is you take these two pieces separately. There's something called a sum rule, which states that the derivative of something plus something is just you take the two derivatives separately and add them together. That's it. And also, we are adding this 2. If you take a function and you multiply by 2, the slope becomes 2 times steeper. So this 2 will go on to the derivative. So what you do is, x cubed, we can see the derivative is 3x squared. X squared, the derivative is 2x, but we are multiplying by 2. So it's not 2x, it's 2 times steeper than 2x, which will become 4x. So like this, we can already do with this one power rule some basic arithmetic with the derivatives. We have taken some random function I came up with this spot here, and we have found how fast it changes. Now, you might be interested in figuring out some more basic derivative rules. Calculus, half of calculus is figuring out what the derivative rules are and how to find derivative for any random function and throw at you. So, to find that, we need 2 principles. One is figuring out what the derivatives of some basic functions are, like sin x, cos x, etc. The other key portion is figuring out how to combine those. So, if you know what the derivative of x squared is, and you know what the derivative of sin x is. Sin x is easy, I can show you in a moment, but if you know that, can you find the derivative of x squared times sin of x? That will be harder, huh? So, you will need some rules for combining derivatives together. And there are 2 important rules, power rule and chain rule. So, product rule is the first rule that we are going to do. Product rule. And I'll just do the statement from the beginning. And I'm going to use some notation for the product rule. Let's say h of x is equal to f of x times g of x. And you already know derivative of f, derivative of g. You can look up f and g in a table of derivatives, but you want to figure out h product, multiplication. Now, I will use this notation h prime. Prime means the derivative. H prime of x, prime is a dot, is equal to f of x times g prime of x plus f prime of x times g of x. And common way to remember this is left d right, left times the derivative of the right, plus right times the derivative of left. So left d right d left. Left d right d left is a common way to remember the product rule. So this might seem like some random symbols algebra. But again, if I do geometry, it becomes way simpler to understand. What I have here, I have some f of x and some g of x. And each of the x's I'm increasing by some dx. Now what would happen then? By definition, the derivative of f of x is going to be the rate at which adding the dx changes f of x. The rate at which it changes. So if I add dx, this length here, when I increase the dx, this extra length will simply be dx times the derivative f prime of x. Dx times f prime. But g prime will have a different derivative, and so the extra length that we add here, dx times g prime of x, will be a different value. So the question is now, what is the total amount of error that we add here? Now again, this one here is just dx squared, we can ignore this. So, what is the area of this rectangle over here? You can see on the plot. Dx times f prime of x times g of x. And so the area of this f. So we are taking this rectangle with height gx and we are adding dx of width, f prime x of width. So the extra width we add will be this times the height that was already there. And the opposite thing happens here. We add dx times the g prime of x times the width, which is f of x. So we divide by dx, cancelling all of this, and we are left with this. Left divide by left. Now I'll just give you some more basic functions to work with, which is just the trigonometric functions. And after that, I can ask you some more questions. So you might have seen trigonometry in context of triangles. Now what we'll do is we'll plot trigonometric up on a graph. So we take the function sine of x. When we take sine of 0 degrees, sine of 0 is 0, right?
Yes.
But as we increase towards sine of 90 degrees, the function goes up. But after sine of 90, it goes down and eventually goes negative and then goes back up. This is sine of x. Meanwhile, cosine of x. Initially, cosine of 0 degrees is 1. But as we go to 90 degrees, it goes down and down and down until it's 0. Then it continues going negative before, after 180, cosine turns around and starts going up and up and up until it becomes positive after doing full circle, and then cosine of 360 is same as cosine of 1, which is just 1. So we have these two curves, sine curve and cosine curve. Now, as I mentioned, this is sine. The derivative is just how fast a function is changing, or the slope of it. You can see the slope visually on the graph. So what do you think derivative of sine will be? It has to be some function that at the start is very high. because the slope of sine on the graph is very high. But here, the derivative of sine has to be 0 because it's not moving. And for all of this, the derivative of sine has to be negative because the slope is going down. And after this here, the derivative of sine will be positive because the slope is high. Can anyone tell me a function here which happens to be high at this point, happens to be negative for this whole range and positive after this? I have just described cosine of x, right? So you can see the second curve I have written here, cosine of x, happens to be how sine of x is sloping at any particular point. You can see here, at the point where sine of x is going upwards, cosine is high. If sine of x is not changing, if it's flat, cosine is 0. And if sine of x is going down, cosine is fully negative. So the derivative of sine of x is equal to cosine. I can just write here. And cosine, you could also think of what the derivative of it have to be. For this whole section, cosine is sloping down, so derivative would have to be negative. But at here, it's flat, and here is flat. So zeros will be here. Will be negative for this whole section, and then positive for this section as cosine goes up. So the derivative of cosine will have to look something like this. It's 0, then negative, then 0, then positive. But this is just minus sine of x, if you look and understand. So therefore we can say that the derivative of cosine is equal to minus sine of x. So now what's the derivative of minus sine? We continue this. Minus sine derivative is clearly minus cosine, because we are multiplying this, both sides we are adding minus. And minus cosine, derivative will be minus minus sine, which is this positive sign. So we have this cycle, sine, cos, minus sine, minus cos, for finding derivatives of the trigonometry functions. So now, using all that we learned, I can ask you a complex question like, what is the derivative of x times sine of x? And we can solve it. X sine x, I'll solve it right here. We did left dy. So x left times the derivative of the y, cos x cos x. And then we add right dy, which would be sine of x times the derivative of x, where the derivative of x is just 1. Hence we have this version, x cos x plus sine x. So we can take complex functions involving x squared, power, trigonometry, and we can find the derivatives. But what we've not learned is how to find the derivative of sine of x squared. How would you find the derivative of that possibly? We are putting two functions inside of each other. Sine of x squared, squared and sine are layering. I have not told you yet how to find that at all. So this is where the last most important rule of derivatives comes, which is chain rule. And chain rule tells you how to stack all these functions in any way. So concept of chain rule is, if I know f of x and I know g of x, how to find the derivative of f of g of x? So what we do is we essentially have to crunch the algebra here. So we can try to do a little bit of intuition, but here's the concept. We are trying to find derivative of f of g of x. We have this which evaluates to a certain question. And the question is, if I increase x inside by some dx, if I by timing dx I increase x, how will this whole increase by? So if I increase x inside of g by dx, we all know what the result will be. It will just be gx plus the derivative times the change. You need to be comfortable seeing this. When I add dx, the change to the overall will be dx times this. G prime x is the ratio between what I change the inner value and what the resulting value comes out. That's what G prime means. So if I add a little bit of dx to this, we get this expression. And now the question is, I've added this. I've not only added dx, but I've also added dx from G prime of x to f. Now what will be our result? Well, we have to multiply this by whatever the derivative of f is at the main point, ignoring the dx. If we ignore the dx, what we have is gx, not g prime x, but just gx. So, what we eventually get is that we have to evaluate the derivative at g of x. And then we multiply that by g prime of x and multiply by this dx over here. Dx gets cancelled and we get this. This is the chain rule. It says that the derivative of f of g of x of outer and inner is equal to the derivative of outer taking the normal inner multiplied by derivative of inner of f prime times gx without the prime times gx prime. So this is the chain rule which allows us to compose functions together. So we now have the key rules. What is power rule? Power rule I've written right here, xn equals x to the n minus 1. And for product rule, can you remember that thing I told you to remember the product rule? What was it? Left the right plus right the left. Left the right plus right the left. So we've done a lot this far. We've shown you, I'll give you some time to note down this. Just note down the chain rule as well. Lefty right right there, and you should remember the chain rule, f prime g of x, g prime x. Now, what I'll show you as the more interesting part, which lets you solve problems, is this thing called implicit differentiation. Now, differentiation is just what we discussed so far. The process of finding derivative is called differentiation because you're finding the difference in functions of changes. Implicit differentiation is taking derivative of an equation, not of a function but of a raw equation. And I'll give you an example of a problem that may involve implicit differentiation. I have a ladder which is angled on a wall. And the ladder bottom is 3 meters away from the wall, just like this 3 meters. And the ladder height currently is 4 meters. Now, I have triangle, right triangle, 3, 4. What's the length of this? 5. We use Pythagorean theorem. The total length of the ladder is 5 meters, of which 3 meter distance is covered on the ground, 4 meters is on. But ladder is not stable. It is falling. Top of the ladder is falling down at distance of 1 meter per second. The question I want you to answer is, how fast is this bottom of the ladder moving right now? It may move at a different speed over time, but at the current moment with these configurations, how fast is it moving? You can't solve this thus far because this is not a function. I'm not defining a function anywhere. I'm just giving you these two values which are connected. But we can use implicit differentiation to take derivative even without a function. So what do we do? Let's say this distance is called x and this is called y. And this is the hypotenuse. Pythagorean theorem, we know x squared plus y squared equals hypotenuse squared. Hypotenuse squared is 25. And for verification, 3 squared is 9, 4 squared is 16, 5 squared is 25, 9 plus 16 equal to 25. So, in general, I can write this formula, x square plus y square equals 25. So it's not a function of anything. I could rearrange this like you saw linear equation. I could rearrange this, say y square equals 25 minus x square, do algebra for 10 decades. But the simplest solution is to imagine that we increase x by some dx and we increase y by some dy. Then what will happen? Well, these will change by some values. In fact, we know that this will change by 2x times whatever the dx is. And this will change by 2y times whatever the dy is. The sum of squares will change by some amount. But the sum of squares can never actually change. It has to equal 25. This is unchanged. So what we will do is, x square, we know the derivative is 2x times the dx that we have. Similarly for y squared, we get 2y times dy. And we equals 0. The derivative of a constant is 0. Derivative of 25 or any number is 0. Because it's not changing. It's not moving. The rate of its change is therefore 0. So we have this formula which states that whatever your dx and dy are, they will change these. But it has to satisfy this equation. Dx and dy have to always be solutions. And we can plug in solve the equation. We can divide both sides by 2, so these 2's go away. X is 3y squared, so we can pretend that 3 times dx plus 4 times dy. I know dy, the rate which y is changing, is equal to minus 1 meters per second. 4 times minus 1 is equal to 0. And from here, can anyone solve this? 3 times dx, the value we want, plus 4 times minus 1 is 0. So, the speed at which the bottom of the ladder will be removed, we will solve this and come up to 4 by 3 or 1.333 meters per second, which you can say seems logical. This is moving at a higher speed than the top of the ladder. So, we have this implicit differentiation to solve an actual physics problem. No, it's good that you're talking, thinking about the problem. It's good that you're thinking. So we found two quantities that are linked together and we are using implicit differentiation to solve a real question. So we have found the derivatives of some common formulas and we have learned the power rule, x to the n equals mx to the power n minus 1. We learned the product rule, left to right, right to left. And we learned the chain rule, f prime of g of x multiplied by g prime x. So now, madam, may I ask how much time I reasonably have? Because there's a complex point that I'd like to see if I can cover now. Maybe we can cover, but we can also cover on Monday if I don't have time. We have time right now? 10 minutes. Okay, so 10 minutes might be a difficult amount of time to cover what I have to say. So may I just give a few problems for you to use what you've noted down. And the next class, what I'll try to begin with is by stating the exponential problem. No, you all, these are just going to be simpler problems. So ma'am is suggesting me to continue with the topic. So fine, I will not give any importance. I will continue with the topic. I will not give. Ma'am is suggesting. You can blame her if you have any issues, not me. I'm messenger. So that we have to cover. What we will now cover is derivative of exponential function. So previously we covered derivative of x raised to power 2. Now the question we want to answer is what is the derivative of 2 raised to the power x? Well, we have the function, the formula that we had before. So we can write 2 to the power x plus dx minus 2 to the x the whole over dx. Now in exponent laws, you can see that this is just 2 to the x times 2 to the dx minus 2 to the x times 1. So when you use exponent's law and you distribute it, you get 2 to the x times 2 to the dx minus 1 divided by dx. And the interesting thing is that we found that the derivative of 2 to the x is equal to 2 to the x times some other stuff. But what is important to focus is that the derivative of 2 to the x is proportional to 2 to the x itself. It's not proportional to 2 to the x over x or 1 to the x or anything else. Exponential functions have the amazing property that they are proportional to the own derivative. So if something is growing at exponential rate 2 to the x, the speed which it is growing is also exponential. And the speed which the speed it is growing, acceleration is also exponential. Now it is proportional but it's not equal. There's still this 2 to the x minus 1 over dx. And we are taking dx as very, very small, close to 0. So you have to find what this constant is. And there's no way of finding this to the algebra. So we use the innovative, astounding technique of just writing dx as 0.0001 and putting it in a calculator. And using this groundbreaking revolutionary technique, we find that this, for very small values of dx, is equal to or approximately equal to 0.69. But it is just 0.69 and some infinite digits. It is some random value. So we get 0.69 times 2 to the x is the derivative of 2 to the x. Now you may try to wonder, where does this 0.69 come from? What is this value? And God damn it. What you can do is you can solve this for other value. You don't have to do 2 to the x and put 2 here. You can put 3 here, or 8 here, or any other value here, and you can find what this approach is for very small values of dx. You can find what this constant approach is for many different values. And what you'll eventually find is that there's some special number where the whole thing evaluates to come exactly 1. There's some special number where when you do this calculation to basic log dx minus 1 for dx for small dx, this comes to exactly 1. And that number we define as the number e. So do not ask where e comes from or why is e like this. E is the number such that e to the power 0.00001 minus 1 divided by 0.0001 is equal to exactly 1. E is defined as the number which solves that. And E is not some normal number. It is some 2.7182818459045. This is what I memorized. But you don't need to ignore this. You can just take E as 2.7. Yeah. E is somewhere close to this value, approximately. E is an irrational number, just like pi in the circle formats. Just like pi, it is defined as being the solution to this. It's not anything else. We don't know where it comes from. E is just defined as this number, the special number E. Now, we know that 2 3x, derivative is 2 3x times this. And derivative of 3x is 3x times this constant for 3x. But for e to the x, we know that this for e simplifies to 1. So, we get this amazing thing that e to the x prime equals e to the x. The derivative of e to the x is equal to e to the x. Exactly. And this is a very important property of the function e to the x for the after number e, that it is its own rate of change. The slope that it increases at every point is exactly equal to the value of the function itself. Now, how many of you perhaps are familiar with logarithms? Some of the higher grades are familiar with, but I will say, we have this thing called a natural logarithm, which is notated as ln. So ln of, let's say we have ln of 2. ln of 2 is defined as the special number such that e to the power ln of 2 is equal to 3. In general, e to the power log of anything equals the same anything. That's the definition for logarithm. Then ln, the log, is defined as the number you need to put e raised to that power so that you get out the original number. And again, not just you can put any number here in the ln function and you get the result. ln because the original term is logarithm, and this is the natural logarithm. You can take other logarithms like the logarithm of base 10 or logarithm of base 2. But what we just did is the logarithm of natural, because e is the most natural exponent. Because this is equal to 1 for e is a natural number, which is why we take the natural logarithm of ln. So now, let's say we have 2 to the x. So we can take e to the ln of 2 times x. If you know exponent laws, you can know that this we can expand to be equal to e to the power ln of 2 the whole raised to the power x. But this section, this is going to be 2 by definition. So we get 2 to the power x. So e to the log 2 times x is equal to 2x. So now, if we want to find mathematically where this constant comes from, well, we can do it. We want to find derivative of 2x. That means find derivative of e to the log base 2 times x. And we can use the chain rule again. The chain rule says that first we take the derivative of the outer. Outer is e to the x. Derivative of e to the x is e to the x. And then you take the normal inner, which is just log 2 times x. And then you multiply by the derivative of the outer, log 2 times x. If I have the line log 2 times x plus 0, the slope of that line will be log 2 times x. It's increasing by log 2 times x. So therefore, the derivative of log 2 times x is log 2, and we multiply this by log 2. But we just showed that all of this, e to the log 2 by x, is just 2 to the x. So we know that the derivative of 2 to the x is equal to 2 to the x times log of 2. And log of 2 is where this constant comes from. This 0.69 etc. is just the natural logarithm of 2. 2 raised to this number will be equal to 2. And this is where the concept comes from. In general, derivative, the rate of change of any exponent basis of power is equal to that same thing times log natural logarithm. And E is just defined to be the base of the logarithm. The one number where natural log of E is equal to 1. And that is where special number E comes from, and that is how to find derivatives of exponentials. So, this is what an important special fact. I'll just revise what we learned today. We have covered what the calculus is, the earliest history, how it needs to change in some concept, how Newton and Leibniz independently figured out that you can take a function and find slope at a given point with the derivative. And we covered some basic things for finding things, the power series, sine, cos, and exponentials. And we learned about the product rule and chain rule, which allows you to nest everything together. So, in theory, I should be able to give you a problem like x cubed times sine of x squared, the whole 2 to that power, and have you solve the derivative. And for today's homework, you will not do that because I'm not evil. I'm not going to make you do that. Derivative problems are especially hard, but we made a lot of progress today. So hopefully I'd like to call it time here, madam. Next class I'll attempt to cover integrals and Taylor series in the next class, but I'd like to call time for this session. You don't need to be that one.